So my name is Bill Buchanan, and I lead a podcast series on the world leaders in cryptography. And today I have a true world leader, Kenny Paterson. Hi, Kenny.
Hi, Bill. How's it going?
Very good. Where are you in the world?
Right now, I'm sitting in my living room in Zurich, looking over the city up on the hill.
Beautiful. In a beautiful sunny day, as it is in Edinburgh. So you'll be glad to know that. We've had some strange weather recently, but the sun seems to have appeared again. So Kenny is a professor in the Department of Computer Science at ETH Zurich, and he leads the Applied Cryptography Group. He was previously a professor in the Information Security Group at Royal Holloway, University of London. Kenny served as a co-chair of the IRTF's research group on cryptography. And from 2014 to 2019, he was the editor-in-chief of the Journal of Cryptography. He was selected as an IACR Fellow, very prestigious award in 2017, and was an IACR Distinguished Lecturer in 2025. Kenny obtained his PhD from Royal Holloway in 1993, and his doctoral supervisor was Professor Fred Piper, who we'll talk about a little bit later. He has been awarded a number of awards for his research work, including the Applied Network Research Prize from the IRTF in 2013, and the award for outstanding research in privacy enhancing technologies for the work with Mihir Bellare and Phil Rogaway on the security of symmetric encryption against mass surveillance, a paper published in Crypto 2014. So, what's your current role and what does a typical day involve for you?
Ooh, that's a good starting question. My role currently is as a professor of computer science. So I'm involved in teaching and research, and as many of your listeners will know, academics are also running universities, so there's a lot of administration to do. Um, and I guess until the end of 2024, I was the head of department at ETH Zurich in computer science for a 2-year stint. And my reward for that was to have a sabbatical in 2025. So I've been in this kind of slightly strange evolution from being a head of department to having no responsibilities to now, as of January the 1st, being back just to being an ordinary professor with all the usual things that go along with that. Right now, we're in the semester break, so the students are not around, so we're not teaching. And that enables me to focus a lot more on research. So actually, on Thursday this week, we have the deadline for the CCS conference, which is one of the big
Mhm.
security
Yep,
conferences.
yep.
And so I'm working on like 3 different papers in parallel for that, and also working on 2 papers where we have to make the camera ready version, which is like the final version for publication this week. Also, the same deadline. So for Usenix security. So it's like 5 papers running around in my head at once. I'm a bit scrambled, to be honest, but
Yep.
let's see.
And which languages do you speak? I assume that you
Oh,
teach in English.
yeah. So ETH is interesting. The first year is all in German.
Mhm.
And then gradually it switches into English as the years go by.
Wow.
And my German is getting better and better. So I've been in Zurich now since 2019. And I did speak German before I came. And then it's improved as I've gone along. And so I'm at the point now where if I were braver, I could teach in German, but I would need to really learn all the specialist vocabulary and then, practice a bit more. But I could do it. Um, yeah, and I speak French as well. I learned French in
Yeah.
school in Scotland, which, a lot of people
Yeah.
learn French, and
Wow.
it's pretty rusty now. And my English is okay, I guess. I do have an accent in English.
Mhm.
Some people find it appealing. Some people think I'm American, but, I'm Scottish by birth.
Yeah. The old alliance, as we would say, between
Yes,
France and Scotland
that's right.
overall. And
Yeah.
yeah, I assume at school you probably didn't learn as much German and French as you probably need now, and that most of it you've learned as you have with your new university.
I think a lot of my French is it's there somewhere in the back of my mind,
Mhm.
and maybe after the right glass of red wine, it might
Yeah.
start to come back a little bit. But it's what's called schoolboy French, right? So
Yeah.
it's like I can buy a coffee or order a train ticket, but I couldn't, or I can talk about the weather, but I couldn't really talk about current affairs, in the way that a French person really would, with kind
yeah,
of natural language and grammar, and the kind of slang that people use.
yeah,
So I know my limitations.
yeah. It's a great environment to bring up kids, I would think, for them to have these three languages,
Yeah,
and it's obviously the right time, and it becomes a chore learning in school if you don't see the relevance. But obviously in
true.
Switzerland, it's so important to learn because I assume TV is in different languages too. If you want to watch a
Absolutely.
football match, then it's typically, say, in German or French.
Yeah, and a lot of people also have international cable television. So
Yeah.
a lot of people I know who are native Swiss actually watch BBC, for example.
Oh,
Um,
great.
yeah, and in school as well, kids speak. There's Hochdeutsch, which is like formal
Mhm.
German that you learn and speak in class. But in the playground, they're speaking Schweizerdeutsch or
Oh,
Zürichdeutsch, which is it's a dialect of German, but it's sufficiently far away that it's almost a separate language. So kids
it's
grow
great.
up learning even more languages than you can imagine. So I've got friends who are, she is Dutch and he is Iranian, and
Oh,
their child is growing up here and going to
lovely.
the kindergarten or the Kinderkrippe as it's called, and is learning Zurideutsch there, but also English at home. So like four languages in parallel. So yeah, it's amazing what the human brain can do actually when it comes to learning multiple languages at once. But
That's great. So
yeah.
what were your school days like? I mean, what kind of subjects
Oh,
did you enjoy at school?
well, it's a very long time ago, Bill, and I'm sure schools have changed a lot since I was there. So I started school in 1974, I think, probably something like that.
Mm-hmm.
I went to state schools or comprehensive schools in Glasgow.
Yeah,
I
yeah.
grew up in Glasgow from the age of 4.
Oh,
It was a very mixed school in the sense that there were kids from all different kinds of backgrounds there, lots of middle class kids, but also lots of kids from very strong working class backgrounds. That was still a time when Glasgow just about had heavy manufacturing.
mm-hmm.
So there were all kinds of different people there. There was also a growing immigrant population in Glasgow at that point, people coming from places like Pakistan and India and integrating. So it was a kind of my school was a real melting pot, both in terms of race, but also in terms of class. And I would say it was not an easy environment to be a young guy with very gangly, with glasses, and very very smart. A lot of snowballs were thrown at me in the playground. Let's put it like that. But I think I survived, and
Mm-hmm.
eventually I got big and strong, and then the snowballs stopped arriving for some reason. I'm not quite
Yeah.
sure how.
And so what sparked your interest in maths and cryptography?
Yeah, it's kind of a long story. I'll try to give the short version. When I had some pretty inspirational teachers at school in physics, actually, and
Mhm.
chemistry. And also in English, I had the most amazing English teacher, who I think her name was Mrs. Campbell, but we always assumed that she was some kind of spinster. And she did Shakespeare with us, and we read modern poetry, and she made us stand up and speak to the class and write these essays. And she was a real what you would call these days a grammar Nazi. So she was very keen on making us write proper, well-formed sentences and put our punctuation in the right places. And so I think I owe a lot of my kind of future academic success to my ability to write well and to tell a good story around a paper and write an attractive introduction to a paper. And a lot of that really comes from her. But on the science side, I went to university to study physics because I was kind of obsessed by this idea of understanding the fundamental nature of the universe, which is how physics sells itself, right? It's very good at marketing itself in those terms. And I used to watch a lot of science programs on TV. Maybe you remember, some of your audience might remember Horizon, which was used to be on BBC Two.
Yeah,
It was like a science
yeah, the
program.
documentaries. Yeah,
Yeah. So I grew up watching these programs about what were they called now? The missions that went out to the outer planets, Uranus and
mhm,
Neptune and so
yeah,
on, and Jupiter. Voyager. Yeah, I remember, and like being fascinated by, the scale of space and how could we explore it and so on. So physics was my thing. But eventually I kind of got more attracted by the purity and the kind of hard, concrete guarantees that mathematics could give you, more so than physics. I learned after a couple of years of physics at university, there's a lot of model building going on. And like each year they would say, forget all the physics we taught you last year, now we're going to teach you the real physics. And it never was, right? You never kind of got to this end
no,
point. Whereas mathematics was like, no, there's a theorem and it has a proof. Of course, at that time, I didn't know about things like Gödel's incompleteness theorem or, some of the logical fallacies that exist and the challenges around axiomatization of mathematics. So like I was kind of a naive young mathematician at that point who thought that mathematics would give me that kind of certainty that I was seeking. So I actually switched from focusing on physics to focusing on mathematics. And I had a little dalliance with computer science as well because I was a home computer enthusiast. This was in the early 1980s. And then I had a BBC Micro at home, which was like the
BBC
best
Micro.
investment my
Yeah.
parents ever made.
Wow.
I learned to program there. I learned pretty much everything about kind of modern procedural programming on that computer when I was about 13 or 14. And actually, so I got to university and did 1 year of computer science, and I sort of dismissed it as being too easy and trivial. And like, there's nothing here to do because like I know how to program already. But there, also missed this idea that computer science was more than software engineering, right? It's about complexity theory or, Turing completeness or, these kinds of uncomputability results, all of that kind of thing. It wasn't really strongly emphasized in that first year at university. So I sort of also didn't really get a grip of what computer science was until much, much later. So I ended up doing maths, but I was also always interested in this like computers and using maths to do things. And I took a final year option in my fourth year at the University of Glasgow that was all about coding theory and cryptography. So using maths to solve these kinds of problems in communications. And I just found it really intriguing and fascinating. Um, and then I wanted to do a PhD and I applied to lots of different PhD programs. And then I met a guy at a party at my brother's house. My brother had just moved into a new apartment, a new flat in Glasgow, and he was having his housewarming party. And one of his friends was a guy called Keith Martin, who you might
Yeah.
know from
Hello,
Royal
Keith.
Holloway, right? And
Yeah.
Keith had already
Professor.
started his PhD at Royal Holloway. And I was talking to him over
Oh,
a beer, and he
right.
said, "Well, why do you come to
Yeah.
Royal Holloway and have a look?" So that's really how I fell into the kind of Royal Holloway orbit, and ended up doing my PhD there.
Yeah. Egham. Egham.
In Egham,
Nice.
yeah.
Nice.
So I had to
Nice.
move from
Nice
Glasgow
area.
to London uh,
Yeah.
at the end of my undergraduate degree. That was like also opened up a whole new chapter in terms of, self-development and exploring London and the whole culture there and everything. So it was great.
It's quite far out of London. I think it's quite
Yeah.
near Heath. Is it Heathrow? I used to go
Yeah,
to
it's the other side of
Heathrow
Heathrow.
first. Yeah.
Yeah,
Yeah.
exactly.
You can hear the planes
You
going over
can, you
a
can.
lot of the
So it
time.
advertises itself as London's country campus, and yes, sort of,
Yeah,
really.
it is. It's a very
But
affluent area, as I know.
yeah, but it's a bit of a trip out from the center of London, and I think it's a little bit misleading to call itself a London university, but it kind of is. So, it formally
Hmm.
is. Yeah. So I spent 3 very happy years there doing my PhD, and also I also had like an industrial scholarship thing as part of it. So I used to go
Excellent.
work for Hewlett Packard Labs in Bristol.
Oh,
They had a
wow.
very
That
good
was the top
connection.
labs.
Yeah,
Yeah.
it was an amazing place to work, full of very smart people. And they gave me the problems to work on that they couldn't solve. And somehow some of them I was able to solve, and that kind of really cemented in my reputation there. I was kind of lucky. I just had this like different set of tools in my toolbox that I could use to solve some of the problems that they had had lying around for a while. So that was great as well.
Yeah. Yeah, and it's a bit like in the US. You see a lot of great cryptographers coming through the New York research labs for IBM
Mhm.
there, and a lot of them really enjoyed the time. Really, uh, they left academia to go into industry, and they actually found it was a better environment for them. Obviously, better paid overall. But HP
Yeah,
used to be such a great research organization. We used to have one, I think, in South Queensferry in
right.
Scotland, who
Yeah,
used to do a lot of the RF work that they did. That's when HP was more of a engineering
yeah.
company, less of a kind of computer printer
Mhm.
company. They kind of lost their way when they called themselves HPE. At one time, they
Mhm.
were a proper engineering company with real sort of depth in their experience. And obviously, cryptography in telecoms would have been a big area for them. So you did very
Yeah.
well. And it was
Yeah.
there you met Fred Piper. So what's your memories of Fred?
How much time do we have? So Fred was formerly my PhD advisor, but what Fred did was really assemble a very nice group of people who worked together to supervise all of these PhD students. So there were people also there like Chris Mitchell and Peter
Hmm.
Wild,
Yeah.
Sean Murphy. who I worked with quite a lot during my PhD. In fact, I worked probably more with Chris Mitchell than anybody during that time. Chris is still there, actually. I think he's long past
Yeah,
retirement
yeah,
age, but
yeah. I know, Chris.
still going strong. So he really became kind of a mentor for me and helped me, how taught me how to write papers and so on. But Fred was always there in the background, and he was the kind of like the mastermind who was like doing a lot of the discussions with the government, with industry, the banking sector, bringing in some of the money, helping to establish those kind of academic industrial connections, engineering the kind of opportunities that I got to go and work at HP, for example, in the labs. But he was also a little bit of a mysterious figure and a little bit distant during that phase, during my PhD, because he was just so busy all the time and he was always flying hither and thither and didn't necessarily have a lot of time to have like a direct technical a research discussion with the students that were there. I got to know him much better later on when I returned to Royal Holloway first as a postdoc and then actually later as a lecturer and then eventually a professor. So in my third incarnation at Royal Holloway, I was there from 2001 to up to 2019. And during that time, I was more of I wouldn't say I was an equal, but I was also on the kind of academic staff and then spent a lot more time and like, went to visit various companies with him, rode shotgun or drove him around and just spent a lot of time and got to know him. We talked a lot about football and
Yeah.
about like he could have had an alternative career as a professional football coach, right?
Ah,
That was his
is that right?
alternative path. And
I don't see him with the long hair. I suppose
yeah,
I
well,
could
maybe
see him
not with
from
the
the
long hair, but
1960s.
in the 1960s. But yeah, he didn't have to be. I mean, he was an incredibly talented mathematician, obviously,
Mm.
but he didn't have to pursue mathematics. He had other options open to him. So what I remember is just a very kind guy who had a lot of time for people and people at that time, so this is like in the late 90s, early 2000s, there was a lot less academic research going on in cryptography and security. There were many fewer research groups and departments in universities in the UK. So it was really Royal Holloway, and then there were some people in Cambridge, Ross Anderson, and so on. And
Yeah.
then eventually Bristol got going. But for a long period of time, Royal Holloway was the only place. And Fred was really at the apex of that. And so he became a very trusted source for a lot of people in industry and government. And the people talk about the reality distortion field that the Apple founder Steve Jobs had. Like he could make people see the world in a different way and bend them to his reality. Fred also kind of had that skill. Like he could sit very quietly and not say very much, and then at the end of a big long discussion, just say a few sentences, and everybody would nod and say, "Okay, good. Now that's what we're doing." Particularly when talking to people from industry, he just carried so much authority, but in such a quiet way, and it was really a unique combination.
Yeah.
Um, so I never
And,
tried to be like Fred because I think it's
no,
impossible. You just have to be,
impossible.
you have to be
Yeah.
yourself.
Yeah, yeah.
Yeah.
Because that was the days of information security before we used the term cybersecurity.
Right.
And I think in
Exactly.
Royal Holloway, uh, they hung on to the MSc in
Mhm.
information
Yeah.
security. And really, it's a better term. Cybersecurity is like 54 different roles and so on.
Uh,
Information security was better. And I think
mhm.
he laid the foundation in the UK for making cybersecurity information systems a respected role, a
Yes.
respected role. I think he started the ISSP,
Yeah,
and he worked
exactly.
with
Yeah, he was
GCHQ
co-founder.
on defining the
Mhm.
standards that you would have for people in that profession, as you said before, it was even a profession
Exactly.
overall. So he did
Exactly.
so much in that foundation. I think there's
Yeah.
even an award. There's some medals that are now awarded with
By him.
Fred. So
Yeah.
we miss him greatly, and Ross Anderson too did amazing work, especially in symmetric key cryptography. But he was a real leader there too. And it seems like the UK is kind of leaking a little bit its
I,
intellectual ability. I see lots of UK academics leaving to go abroad to big companies. Obviously, the salaries are much higher. But I mean, maybe I'm looking at this wrong, but I think there was a great time for cryptography in the UK, and perhaps it's not quite as strong as it used to be. I may be wrong.
I,
Do you
I
think
would I
that's
would disagree if you don't mind, Bill.
yeah,
I would say that there's
great?
just another
Yeah,
generation is coming
yeah,
through, and
excellent.
there are really strong people in places like
Yeah,
King's College where
yeah.
Martin Albrecht and Ben Dowling.
Martin.
Also, I wanted to mention, at Royal Holloway they have a young
Yeah,
crop of really good
yeah,
cryptographers these days and security people,
yeah,
and I think the state of the UK is okay. It was a little bit dicey there for a while. So Nigel Smart left and went to KU
yeah.
Leuven. And then I
That's right.
left a year after him or 2 years after him and went
Mm.
to ETH Zurich. People often ask me, was it about Brexit? And actually, it wasn't really about Brexit. It's just
No,
ETH just
no.
made me an offer I could not refuse.
Yeah.
Uh, so,
So I think
but
that's my next question. How have
Mhm.
things changed for you moving from a professor at Royal Holloway to ETH Zurich?
I think there's a couple of
Just
big
probably
distinctions.
number one in the whole world.
Certainly number one in Europe, right?
Yeah,
I like
yeah,
to think of it as like the MIT of Europe.
yeah.
And so like I think I didn't realize how big a difference that would make actually, because just in general, the level of ambition is significantly higher than other institutions would be. And the funding is way better. So I have what's called base funding now every year. So back in the UK, as you probably know very well, essentially every pound or dollar that you spend has to come from somewhere and has to be from a research grant or some overheads that you've recycled. I don't want to go too much inside academia and how the funding works, but at ETH, each professor gets given a certain amount of money every year by the university, and it's up to them how they use that money. And so I have enough for a team of let's think now, maybe 6 or 7 people on a
Wow,
constant basis. And then, of
that's
course, you
excellent.
add grants on top of that. So I have a team
Yeah.
now of, I think, 14 or 15 people working with me, plus all lots of master students and so on. And so you can be more long term and you can be more ambitious because you know that you've got this steady income that's going to come every year. Um, and so, yeah, I now maybe try to take on, instead of just thinking about writing the next paper, I might try to think about, okay, what's a project that we can do that might take a couple of years but have a bigger impact and deliver something more substantial. I can give you some examples of that if you're interested. But
Yeah. 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 Go
yeah.
ahead, please.
Well, one would be so for another feature of Switzerland is that there's a lot of international organizations here, including things like the Red Cross or the International Committee of the Red Cross, ICRC. They're based in Geneva, and they have some very interesting, let's say, secure communications challenges. So they go out into the field, and their workers, their people are working in war zones in between the lines, trying to deliver aid and trying to broker ceasefires and so on. And so then they're often working in environments where there's no network infrastructure left. It's all been blown up or jammed. But they need to be able to communicate with each other. So what they need is some kind of, say, mesh networking solution, which is like using just the actual devices that they're carrying to create, some kind of network that they can communicate over. And this doesn't work very well if everybody's very spread out and too far apart. But like if they're all in the same building, some kind of headquarters, maybe you have enough connectivity and enough bandwidth that you could, send an emergency broadcast message saying, okay, everybody to the bomb shelter, or use in if the bandwidth is higher and better, maybe you could use it actually for secure messaging in the way that you might use Signal. So what we're doing right now is working with ICRC and with funding from ETH's Humanitarian Action Challenges Fund and also from our ZISC, the Zurich Information Security and Privacy Center, we're helping to build, to design, prove secure, and prototype a secure mesh networking system for the Red Cross, for the ICRC. And that is taking it's very difficult because it is like a lot of low-level networking stuff, but there's also security and cryptography you have to get right, and then user experience and so on. So there's like many different layers of stuff that you have to build. Um, and I'm able to use resources from ETH and just because of the excitement of the project, build a team that can run with this and do something significant over a period of years.
Yeah.
So hopefully later in 2026, we'll have a working prototype that works at a reasonable scale. And eventually we will hand this over to the Red Cross, and it's something that they hopefully will continue to develop and take forward and maybe eventually get to doing field trials, and then eventually it could become like a supported product that they use every single day. And like I could never have done something like that, I think, in my previous role.
No.
And along the way as well, what's also interesting about that is that there is research involved, and we will write a research paper at some point, or maybe a couple of research papers describing, the challenges that we faced and how we overcame them. But it's not primarily about writing research papers anymore. It's about building something useful for the world.
Yeah,
It's very nice to be able to take that perspective.
very good. Because I think the UK is maybe a bit more in terms of the metrics, in terms of research papers and measuring
Yeah.
output. We have the research assessment exercise every few
Hmm.
years, and it's always a scary time, and it almost
Hmm.
feels like a bit of a game, and
Yep.
that you really should be doing research in your heart and believing in something. So what's your favorite area of cryptography? I don't know if you actually teach at all on a regular basis,
I
but if you were
do.
to teach something, you do?
Oh yeah.
Yeah,
I,
that's
I
great.
actually I'm going to be in a month from now. I'll be teaching
Mhm.
cryptography twice in parallel, once to
Excellent.
undergraduate students and once to master's students.
Yeah.
So two different levels of crypto. In both cases, we're trying to give them a flavor of like the core parts of cryptography. So some symmetric key stuff, some public key stuff, some key exchange examples, and then maybe talk about how TLS works and how Signal works. So that's what I'm teaching because I feel like I don't want to teach the latest, greatest research. I want to give them things that they can carry with them into the
Yeah.
world when they become software engineers. Uh, but to answer your question, what do I get excited about cryptographically? I think probably I'm well known for working in this kind of intersection between theory and practice and trying to understand why theory gets misapplied or gets ignored when it comes to practice and what kinds of errors and issues do practitioners introduce and why is that? And then what can we do to try to narrow this gap a little bit and let's say, make theoretical cryptography more practically relevant, let's say. So we do that in various ways, which we'll get into, I think. But that's broadly
Yeah.
where I sit and what gets me excited.
Yeah, you like to break things and then fix them.
I do,
That's what
yeah.
I like to do. That's why I like cryptography. I can break
Yeah.
something and
Uh-huh.
then I can fix it. It doesn't seem good. I'm a hacker if I break it and I just leave it broken, but
Yeah.
I'm an academic researcher if I can actually
Right.
fix it after that.
Right.
So I think
Yeah.
that's a great explanation
Hmm.
actually overall. So there's this thing called pairing-based
Oh,
cryptography, and it's
yes.
almost like some sort of magic. You've got people like Liam Kamenish creating amazing systems with that cryptography.
Mhm.
It's a difficult thing to explain, but could you explain pairing-based cryptography and what its core applications are?
Oh, I can try. So pairing-based
Try,
cryptography
yeah.
is something that really blew up in the late 1990s, early 2000s. There were some very kind of revolutionary papers that came out, one by Bonnet and Franklin, that showed how
Mhm.
to use pairings to achieve something called identity-based encryption,
Yeah.
which was an idea that Shamir had had some years before, maybe 10 years before or so,
Hmm.
but nobody
Yeah.
knew how to build really.
IB. Yeah.
IBE, and they
Yeah.
showed this was actually achievable using pairings. So, and then also there was a very nice paper by Antoine Joux, who I think has been on your series,
Yeah.
or yeah, if he
Yeah.
hasn't, you should get him. But
Yeah.
he's
Yeah.
one of the greats. And
Yeah.
he showed how you could use pairings to realize a non-interactive version of Diffie-Hellman, but for three parties at a time instead of just two parties.
Tripartite. Yeah.
Yeah,
Tripartite. Yeah.
yeah,
Yeah.
tripartite
Diffie-Hellman.
Diffie-Hellman key exchange.
Yeah.
And there was also a paper by Verhul that showed you could use pairings. But anyway,
Mhm.
long story short, they're like it's like doing discrete log-based cryptography, so Diffie-Hellman, but you have this kind of extra functionality that enables you to um, look at relations between group elements and test certain relations between group elements, like quadratic relations essentially between group elements in the exponent, let's say. So
Mhm.
given G to the A and G to the B, two group elements, so you've got some group G generated by a little generator, little g, you can think
Mhm.
about g to the power of a and g to the power of b, and then the pairing enables you to calculate something related to g to the ab, but not exactly, but in a related group, let's say. So it kind of transfers you into a different group, but gives you this kind of ability to multiply a and b together in the exponent.
Mhm.
And this is like it turns out to be fantastically useful in the right hands. So Bonnet and Franklin's paper and the Jus paper really opened the floodgates to people realizing you could do all kinds of cool things with pairings that we didn't know how to do otherwise, or we didn't know how to do quite so efficiently otherwise.
Mhm.
And so lots and lots of new things became possible. Actually, a lot of it is quite applicable, I think, in the blockchain arena, for example. Things like aggregate signatures became possible.
Yeah.
And then people like Jens Groth and others realized how to use these things to make zero knowledge proofs more efficient. and they're very widely used in that domain now. And so it just became this really kind of Swiss Army knife style of cryptographic tool that you could use in all different places. And I was a little bit involved in some of that research. I guess it's what got me more into cryptography in the early 2000s, and I managed to publish some nice research around that time. And then over time, pairing-based cryptography became kind of mainstream, and it kind of disappeared as a. It's still there. People are still using pairings a lot, but it's not kind of like a special topic in its own right any longer.
No.
We organize
Mhm.
some conferences, for example, like the International Conference on Pairing-Based Cryptography, but quite rightly, that conference is dead now because pairings are just this kind of universal thing that everybody knows. One of the really interesting things, though, is that they're not quantum secure. They all exist in groups where we know how to solve the discrete log
Elliptic
problem.
curves. Yeah.
Exactly. So the groups that we use for building pairings are all related to elliptic curves, more or less. And yeah, we can solve the discrete log problem there with a quantum if we have a large enough quantum computer. Um, and there's a little bit of like open question of how can you build a really clean, nice analog of pairings that are actually, quantum immune or quantum safe. And
I
that's
asked Jens Groth about that
hmm
actually, because he obviously created Groth 16, which
hmm
I think was the smallest zero knowledge proof that you could actually create. It's been the size has been reduced since then,
Yeah.
but he really broke the ice with that one, and
Yeah,
he
that was a
said
real breakthrough paper.
homomorphic encryption is probably the answer because obviously with the homomorphic encryption with lattices, you can have
hmm
this natural pairing system, but obviously the performance isn't really going to be as good as it
Yeah,
is with
that's right.
elliptic curves.
Yeah.
But we've probably still got 5 to 10 years of elliptic curves work
Well,
still in it.
depends how you think about harvest now defibrillator attacks, but
That's
maybe we
right.
can come to that. We can come to that
Yeah,
later.
that's
So
right.
yeah, so pairings was a thing, and it was very fruitful in the early 2000s.
Mhm.
Yeah, indeed, and then we
Yeah,
moved on to other things.
yeah. And what certificateless public key cryptography? I find that PKI is one of the least understood areas of
Yeah.
industry. If
Uh-huh.
Microsoft can forget to update a digital
Mm.
signature for the Azure cloud and take it offline for a whole day, then you
Mm.
can really see there is some worries about the industry understanding what digital certificates and PKI actually is. So,
Yeah.
what's
Yeah.
certificateless public key cryptography?
Well, let me try to give a fairly reasonable explanation. I guess one explanation is it's a playground for cryptographers to invent new schemes and write papers. So it turns out that actually I co-invented certificateless public key cryptography along with Satam Al-Riyami, who was a PhD student at Royal Holloway at the time, and we wrote a paper, and it now has more than 3,000 citations. So it's like my
Wow.
most my most
Yeah.
cited paper, but
Yeah.
it's also nobody, I don't think anybody's ever used it in practice. I think it's just one of those nice scientific things. And it's like an intermediate between normal public key cryptography and identity-based cryptography.
Mm.
So normal public key cryptography, everybody has their public keys and you need certificates so you know whose key is whose, right?
Yeah.
And that's where PKI comes in. And the other extreme, identity-based cryptography or identity-based encryption, you have a trusted authority who issues the keys, and the key is like a function of your identity and some master secret that belongs to the trusted authority. So your identity becomes your public key in a sense, and there is no need for certificates at that point. But the problem with the identity-based approach is that there is this trusted authority who knows everybody's private keys. So in principle, could decrypt everybody's data, right? And that's okay in certain circumstances, like in a corporate scenario where you want that decryption capability. Maybe it makes sense, um, but it's not really where the world has moved to. And so certificateless public key cryptography is an attempt to kind of thread the needle in between these two extremes and allow you to have systems where you get the benefits of identity-based encryption, so there's no certificates, but also you don't have this kind of built-in backdoor capability. So trying to get the non-escrow capability that PKI offers. And yeah, we succeeded in some technical sense, in some theoretical sense. But I think it's interesting that there's been, as far as I know, zero adoption of certificateless cryptography in practice. People largely stick to PKI-based approaches.
Yeah, but I suppose something like Hyperledger Fabric, which is being rolled out for EID in Europe, where you can
Hmm.
store the public key
Hmm.
on a blockchain. So I think the
Hmm.
way it's proposed is that each country in the EU would actually run their own Hyperledger Fabric infrastructure. The public keys of say ETH would be
Hmm.
stored onto that blockchain. So I suppose that's close to being a certificate-less system where
Okay.
you actually have a trusted authority which is storing the public keys, and it breaks away from this crazy PKI infrastructure that is
Hmm.
run by these
Hmm.
magical companies that have the rights to be able to create that.
Mm.
And it's an interesting thing because I know that Switzerland just voted in no more for the
Yeah,
EID
that's
system.
right.
It's
The Swiss
obviously going
version of it.
to
The Swiss
really
version.
change the Swiss version. Hopefully, there'll be more privacy than we
Mm.
have in the UK. The UK is getting closer, but there's such a kickback on
Yeah.
this. That's really quite worrying, and I
Uh-huh.
worry about the privacy integration. But obviously, we're seeing EIDAS 2 being introduced and then qualified electronic signatures. It's almost like the dream that we've had for 30 or
Hmm.
40 years is finally coming true, that digital signatures will have legal certainty. Do you see the EU uh, evolving, changing? Really, I mean, they want to break down borders and
Yeah.
break down silos and make it easier for people to move around easier. I'm not asking you from a political point of view, but from a
Mhm.
technical point of view, do you think this is an amazing time in the EU just now with this advancement in digital wallets and signatures?
I think there's real progress and there's real momentum behind making this a reality.
Mm.
It's a little bit unfortunate that, and this is always the case with such systems like this, that they don't really incorporate the latest research, right? So they're using techniques that are, could we know better solutions for, but the problem is those cryptographic solutions are not yet standardized, they're not yet supported well in libraries. So there would be an option to make them much more private by using zero knowledge, essentially zero knowledge based anonymous credentials. But they're not really, those technologies are not really there yet. There was a great presentation at Real World Crypto in Sofia last year, exactly about this. I'll try to remember who the presenter was. And she was really giving an analysis of the technology maturity, the cryptographic technology maturity in this space, and it was really quite sad to see how all of these great ideas that we've developed in academia they exist as research papers, but they're not ready for prime time. And I think a lot of academics actually don't really understand that very well, that like it's not enough just to write a paper. You need to write code, you need to build a library, you need to maintain a library, you need to work with standards bodies to build standards. And then gradually, you can build up the case for these things being used in practice. So I think, to summarize, there's like a lot of exciting developments, but it's not using the cutting edge cryptography that it could be. But maybe in 5 years, in the next revision, we'll get there.
Yeah, I think the green passport that we used in COVID times was
Hmm.
a massive advancement, and you actually saw privacy being integrated and so on. And we kind of lost our way a little bit. So, and the
Yeah.
problem seems to be in the legal industry. They just don't want to move away from wet signatures as
Right.
being legal, and they don't quite understand what it is they've got. In Scotland, they're passing Digital Assets Act, which I can't understand because it's all written in legal. It says the word
Mhm.
immutability somewhere,
Mhm.
but that's as far as it goes from a technical point of view. In the UK, I think has just passed a digital assets bill, so hopefully we'll actually start to see the legal industry adopt digital signatures from a legal point of view, so that when you buy a house, I don't know what it
Yeah.
is like in Switzerland, then you'll actually have
Oh,
digital signatures
in
defined.
Switzerland, so we bought a house here, an apartment here in 2024, and you have to go to a notary, and the notary reads out all the documents, and then everybody signs everything. And I think big notary has got a bit of a stranglehold on the signature business in Switzerland,
Mm.
and
Oh, good. Okay.
it's gonna take a while until we can
Yeah.
change that. Yeah.
Yeah. So a good deal of your work is involved cracking
Hmm.
ciphers, so breaking our normal communications. And obviously things like SSH is like the keys to the castle. If
Hmm.
people break SSH, they could break your whole cloud infrastructure. So what type of things did you manage to recover? How did you manage to recover plain text from SSH traffic
Okay, great. So
without
this is
giving
way
away too
back
many
now.
secrets
No, no,
ethically?
no, no. This is way back in 2008,
Yeah.
actually. I
Mm,
had a PhD student called Gavin Watson, who I think was funded by BT at that time. We had a scholarship from British Telecom, and part of that was to look at these modern communication security protocols and figure out how they worked and see what we could say about them. And actually, that whole thing came out of me when I went back to Royal Holloway as a lecturer in 2001, being asked to teach network security, or rather being told to teach network security. And the only part of network security I could understand was like where they were using crypto to do things like SSH or SSL as it was at the time, IPsec, so on. So gradually this bled into my research and became like a research topic. Like what can we say about the security of these systems? And we were amongst the first people to do that. But there was actually a paper before ours by Bellare, who you
mhm,
mentioned in the intro, Kono and Namprempre. So Kono and Namprempre were students of Mihir Bellare at San Diego at the time. And they'd done this very nice analysis of SSH and they had proved SSH secure. And
mhm,
we were in the process of like trying to write an entirely different paper and write something in that paper that referenced this other paper by Bellare, Kono and Namprempre. And suddenly we realized, hang on, the thing they're proving about SSH can't be true because there's this extra length field in the SSH packet structure, and that length field gets encrypted. What that means is when you're doing decryption, you can't know how long the message is or the ciphertext is until you've received that field and decrypted it, and then use that to determine how much more data you should receive until you've got to the end of a packet. And what that means is that the decryption process has to depend on the plaintext. Okay. And so what we were able to do was and also the encryption mode that was being used mostly was CBC mode, which you probably know
yeah.
very well, right? So you chain together
Yuck.
these blocks, and it has this kind of malleability property,
Yeah.
which means I can take a block from down there in the ciphertext and I can move it up here,
Yeah.
and it will get decrypted somehow with some errors,
Mm,
but basically I can control how the decryption process is happening. So what we realized is that we could put a block from anywhere in the ciphertext that might contain your password and put it in this position so that when it got decrypted, part of it was interpreted as this length field.
mm.
And then by
Wow.
observing the errors and knowing when decryption failed because it reached the end of the ciphertext and some integrity check would fail, we then could tell, well, what must have been in the length field then? But because of the manipulation we had done moving blocks around, that actually revealed partial information about your password. So it was actually a very novel attack and very, I think super clever, although very, very simple. I can explain it in 3 PowerPoint slides. Um, and it was quite shocking because, there was this provable security analysis that said SSH is now secure. You can use it, without too many qualms. And also this thing was, as you mentioned, this thing is used everywhere, but it had never
Yeah.
really undergone this very serious, low level, byte level, if you like, kind of audit that we did for it. And so then we found this attack, and it the attack was a plain text recovery attack rather than a
Mm,
key recovery attack. But it was kind of on the verge of practicality. So you could recover a certain amount of plain text, maybe up to 32 bits or 4 bytes, like half a password, with some lowish probability. But you could repeat this attack over and over again against many SSH connections. And then, as a man in the middle attacker, you could attack as many SSH connections as you could find, and you could then start to recover small amounts of plain text. But the goal of these kinds of protocols is to protect all of the plain text all of the time, right? And to have like very, very strong security properties. And here we were saying, here is half of your password. So this was I guess it was kind of a big deal at the time. And we wrote this up as a paper, and it got published in a good conference at the time, even though the attack was very, very simple. And it was somehow the simplicity of this attack somehow was like really a feature, not a bug, right? Because it's like
mm,
the real question is how did the community miss this for so long? And the
yeah.
point was that nobody was thinking about the security of these real world protocols. Everybody was writing the next theoretical paper rather than
Mhm.
saying how good are the tools that we have in the world.
Yeah. It sounds like a bit like the heartbleed um,
Oh yeah,
bug that was caused, and that
right.
the person who wrote the RFC was the person who implemented it, which isn't
Yeah,
never a good
never a good
thing
idea.
to do. But that nearly ripped the heart, as you could say, out of the internet. It could have caused
Hmm.
so many problems. SSH
Hmm.
is such a fundamental protocol, but it tends to be based in lots of old RFCs
Yes.
and
Yeah.
SSL and TLS was never a great protocol anyway. I mean, few people
Mm.
would know that your TLS session is probably broken
Mm.
somewhere with what's
Mm.
called a web application firewall, like a
Oh, right, of
Cloudflare,
course.
and
Yep.
your traffic is being decrypted. Uh, Everybody thinks it's end-to-end encryption, and then often it isn't actually in there. So
Yeah.
the only true end-to-end is to use something like WhatsApp and Signal and so
Hmm.
on. Everything else is a machine-to-machine
That's true.
type connection.
Yeah,
So
absolutely.
in your Lucky 13 paper,
Yeah.
hopefully you remember that one. What were some of the attacks that you
Uh,
uncovered?
so this was now looking at SSL and TLS rather than SSH. So one layer down in the protocol
Mhm.
stack. And yeah, where did that one come from? Or what did we do there? Well, it was a plain text recovery attack again, much like SSH. But this time, it was a timing attack. So rather than observing error messages on the network and knowing for sure that, something had gone wrong and then using that to diagnose something about the plaintext, you had to be able to very carefully time the amount of time it took to decrypt certain packets on the network. But you could actually measure that maybe one or two hops away. So it was like what's known as a remote attack rather than a local attack. It wasn't like you had to be running on the same hardware as the victim. You could be on the network observing timing differences. And the timing differences were very, very small, and they arose from the way in which decryption errors were handled. Um, and actually, really, this came from a paper written by Vodny something like 10 years before. And he had pointed out that there was this kind of new class of attack against these encryption modes called padding oracle attacks, which
Yeah.
arise from the way that CPC mode is using padding to make the message length a multiple of the block size. And he was able to show that this could lead to vulnerabilities because when you decrypt the last block, you have to remove the padding and it could be that the padding ends up being wrongly formatted because the adversary was playing some games by, playing around with ciphertext blocks. And then you would have to maybe issue an error message. And whether there was an error message or not was leaking something about the format of the plaintext. And then that is like a tiny amount of information, but over many, many iterations of this kind of attack, you could recover all of the plaintext. So this was like known, but and SSL or the SSL TLS specification had tried to close this attack avenue, but they hadn't closed it tightly enough. And we found there was still this very small timing difference that was possible. And we called the attack Lucky 13 because in the first version of the attack that we found, there was this like the number 13 played a role if the data was aligned in a certain way. Then the fact that you had 5 bytes of header and 8 bytes of something else, and 5 + 8 is 13, meant that the attack was particularly efficient. But it was also a cool name, right? And actually,
Okay,
I
13.
learned that vulnerability branding was kind of became important at that time. So, but
Yeah.
this was part of a much wider piece of research that lots of people were engaged in,
Yeah.
really trying to understand what security do we get from TLS. And
Yeah.
this research, together with all these other great pieces of work by other people, eventually led to the realization in the ITF that they needed TLS 1.3. And so,
Yeah.
like, the kind of weight of evidence became overwhelming that it was time for a major redesign.
Yeah, I mean, because side channel implementations aren't easy. Just to take the algorithm and to code things up. We saw the problem with the Montgomery. We cracked RSA from radio emissions coming from
Hmm.
a Raspberry Pi in
Hmm.
30 minutes.
Hmm.
This is 128-bit AES.
Hmm.
Um, through this side channel, and because of the Montgomery curve, you
Yeah.
can actually see when something is a one or a zero. So there was a
Hmm.
follow-up paper, I think, called Lucky
Oh,
Microseconds
yes.
in
Yes.
2016. What was that
16.
attack and what was the significance?
Yeah, that was a lot of fun. So that was actually one of my favorite research papers with Martin Albrecht,
Mm,
who I mentioned earlier, who's at King's College
mm,
now. And at the time, I think he was a postdoc at Royal Holloway, and then eventually,
mm,
pretty quickly after, he became a lecturer there. And So in 2015 or 2016, Amazon Web Services brought out their own implementation of TLS
Mhm.
called S2N, which was short for
Yeah.
signal to
Signal to
noise.
noise. Yeah.
Yeah. And Martin and I were actually at the Happy Man, which is the pub in Englefield Green next to Royal
Oh
Holloway,
yeah.
having a pub
Yeah, I know
lunch.
it. Yeah.
And we started talking about this new thing, and he said, it's only a couple of thousand lines of code. And I was like, it can't possibly be secure against Lucky 13 style attacks, like these very sophisticated timing side channel attacks, in only that many lines of code. And like, we should look at that. And so we went back from the pub to our offices, and then we started looking at the code, and we found that they tried very hard to avoid these timing channels, but they had inadvertently introduced one. There was actually a bug in their code.
Mhm.
Um, and so we disclosed it to AWS. Like this was like 3 days after we just worked on this like crazy for the whole week. And I think we sent it on Friday to AWS, and then we had a meeting with them on Monday morning. And they said, you missed something.
Yeah.
We actually add random noise, random timing delays
Mhm.
to the decryption process to hide these
Mhm.
kinds of side channels. So your attack
Mhm.
doesn't work. And
Mhm.
we were like, okay, so how much noise do you add? And they were like, well, we use the microsecond timer to give us an amount of time, and we use that. And then like we looked at each other. Well, we were actually in separate offices, but we had like a side channel through, sending messages. I think it was a
Yeah.
Skype call or something. And we're like, microseconds, but our attack works on nanoseconds.
Nanos. Yeah.
Yeah. So what was really interesting then was if you just took all the timings and worked modulo 1 microsecond, meaning like subtract, just get rid of the microsecond timings, their countermeasure disappeared. Now, not completely, right? Because there's
Mhm.
noise also in the microsecond timers, but essentially you could get past their countermeasure just by working at the right low level of resolution in the timing. So we got to write this very nice paper that basically said, look, they made a mistake here, and then this countermeasure didn't work, and here's the consequence. We can recover plain text. And I think the attack was like very much on the verge of not really being practical, right?
Yeah.
But it would
Yeah.
require hundreds of thousands or millions of sessions to be completed to recover like one block of plain text. But again, the standard that we set for security in this space is very, very, very high.
Mhm.
And this was AWS, which was like one of the strongest security teams. The code was written by a very senior engineer there called Colm O'Hegarty, I think his name was,
Mhm.
who's like a really top guy. And so it was a little bit of a, geek versus geek kind of thing going on. And actually, we worked very closely with them on remediation, and we helped them, or we gave them advice about what changes they needed to make. So it was like actually all very constructive, and we got a very nice scientific paper out of it, which is sort of again um, really going all the way through the entire process and showing that an end-to-end attack, right, taking into account all of the code and the countermeasures and everything they applied. But the biggest lesson of all, actually, for me was like just working with Martin was great, and he was also on the SSH paper back in 2009, so this was like 6 or 7 years later. And he is my most prolific co-author, I think. I think we've got, I don't know
Yeah.
how many papers, 25 or 30 papers together. And it's just great fun.
It's great. Yeah.
Our minds
Because
somehow
obviously,
work together.
yeah, because obviously a lot of companies like Google, I think it's Tink, was really unfortunate library. They rewrote a lot of these libraries because of the heartbleed problem with
Hmm.
OpenSSL. OpenSSL was really ropey. I think there was one full-time person writing the
Hmm.
code. It was
Yeah.
all goes back to this original code, and it
Hmm.
was just full of bugs. So I think
Hmm.
Amazon, AWS, and companies like that decided to rewrite the
Yeah.
stack because it
Yeah.
was a mess overall. OpenSSL has got their act together. I think
Absolutely.
3.5 is looking really good.
Hmm.
It still
Hmm.
has a lot of legacy in
Yeah.
it, and there's methods that go back decades. But I think with AWS, they wanted to write something clean. So I
That's
think
right.
you were doing them a good service to be able to
Maybe.
kick the tires with
Well, they
it.
got a free audit, actually. That's one way of thinking about it, right? From people
So
who are good at this stuff. And
yeah,
maybe we come back
yeah,
to that later. A lot of the time, when we look at real world cryptography deployments, we're kind of providing free auditing services to these companies. And if they're smart, they realize that and they play it in the right way. But you're absolutely right. So, like the big trigger for AWS and also Google to introduce boring SSL And I think
on
there
the
was also
SSL. Yeah,
another fork. It was to do with Heartbleed, and then this
yeah,
realization that OpenSSL was sort of not in great shape.
no,
But again, it's one of those things where like free software or open source software, like gigantic chunks of the web and the internet and like modern society are built on top of these free libraries that everybody is using, but nobody is funding. And
yeah,
I think OpenSSL then had a lot of sympathy from people who understood that they were under-resourced,
yeah,
and that helped them really get more resources and scale up their engineering effort and get to the point where they are today, which you mentioned, they're in a much stronger place than they were around the time of Heartbleed.
yeah,
Yeah,
yeah, much
but it took
better.
a, it took an almost catastrophe
Yeah,
for all of that to happen.
yeah.
Yeah,
In
exciting
cryptography,
times.
we're building on sand with C codes, C coding, and pointers and things like that. So obviously,
Yeah,
there's this
uh-huh,
big
uh-huh.
debate about whether we should move towards Rust. I've
Hmm.
actually been looking at Zig as
Oh,
a programming language, and it's really
uh-huh.
great for cryptography. It's like C, and it can build on any. It's good for embedded systems that you can build for any system that you actually want,
Yeah.
but it doesn't have the complexity of Rust.
Hmm.
So I think it's interesting times just now.
Hmm.
So there was a
And some of the
paper.
big players are also getting into
Yeah,
formal verification of cryptocode. So
yeah, yeah,
Microsoft, AWS, Google all have efforts in that direction, and there's a lot of smaller players too. So that's a really interesting direction that things are going now.
yeah. I attended the OpenSSL conference in Prague
Oh yeah.
last year, and it was really quite impressive the
Hmm.
way they've really got their act together, and the way they're reviewing code and
Hmm.
helping build their libraries overall. And they've
Hmm.
obviously integrated a lot of the post-quantum cryptography methods
Hmm.
in there,
Yeah,
and that should move the industry forward a
absolutely.
good bit. So I think you in your paper Mega Malabo encryption gone awry, you managed to crack an RSA key in 512 attempts.
Hmm.
Why were you looking into Mega, and how did you manage to crack this RSA key?
So, yeah, it's a great question. So, Mega is an online service that offers to encrypt your files for you and store them in the cloud. And it offers what we call end-to-end encryption, meaning that something we referred to earlier. But in the context of cloud storage, it means that only the owner of those files should be able to obtain the plain text. In particular, the cloud service provider shouldn't be able to see the data, right? So they should not be able to decrypt.
Mm.
And Mega had then maybe even more today, but they had about 300 million users when we did this research now,
Wow.
3 years ago. Enormous,
Yeah.
right? They were storing more than 1,000 terabytes of data according to their web pages. So really huge and like kind of unknown, but really, really big. And we just did a kind of full spectrum analysis of how they were using cryptography. And they had done a lot of things. They'd kind of hand rolled a lot of their own protocols. So the cryptography they were using, well, actually, no, it was kind of bad all the way down. They were using good algorithms like AES, but then they were combining them in all kinds of really unusual ways. And this is actually for me nowadays where the interest is. I'm not going to be able to break AES. It's an extremely good algorithm. But people will use these algorithms in all kinds of creative ways, let's say, when they're building their own systems. And maybe that's where the interest is, like how do you plug these components together? So Mega was a great example of this kind of roll your own system. And we managed to do an analysis where what we could show is that there was a login protocol where a user would enter their password, but then there was also this kind of RSA challenge thing going on where the server would send you an RSA ciphertext, and then using your private key as a client, you had to decrypt it and then send back some
Mm.
version of the plaintext. And so there's actually a kind of decryption oracle in the clients, so that the client would use the private key and decrypt anything it was provided, and then give you some kind of response. And we were able to show by carefully crafting the ciphertext that the server sent to the client, that from the client responses you could learn a little bit. You could actually learn one bit of information about the private key for each login that the user did. And then across many, many logins, in fact, we needed 512, you could recover the entirety of the private key. And there's a cute trick
Oh,
there.
there was 512-bit modulus, was it?
Well, actually, it was let me get this right. It was a 2048-bit modulus, which meant P and Q are
Which
both
is
1024 bits.
yeah,
But once you've recovered half of P or
yeah,
Q, you can recover the rest using a lattice attack,
yeah.
right? So there's a very nice technique called lattice cryptanalysis,
Mm.
and this was a an example of lattice cryptanalysis in the wild, which really doesn't come up very
Yes.
much. And
Lystra,
so,
Lenstra.
yeah,
Yeah.
exactly. Yeah, exactly. Using the LLL algorithm.
Hmm.
To compress the story right down to its basics, what we wanted to do was minimize the number of logins that were required because login requires human interaction, right? And we got it down to 512. And that's the best we could do at that point in time. But as you know, not long after,
Yeah.
actually just a few weeks after our paper was released,
6.
yeah, Keegan Ryan and Nadia Henninger got it down to 6 logins from 512. And what was funny about this was like one of the things that Mega had said was, we don't think anybody's customer data was compromised because we looked at our server logs and nobody logged in 512 times. But sure as hell, some people logged in six
Yeah.
times, right? Fortunately, they had patched the system immediately
Mhm.
after we disclosed the vulnerabilities to them. And so this 6 login attack didn't actually have any practical impact anymore. But it showed this thing that attacks only get better with time, right? And
Mhm.
sometimes that improvement comes very, very quickly. And then in another follow-up paper, we got it down to 2.
Two.
And for sure, people logged in twice. That
No.
was in a paper where we were actually analyzing the fixed version of Mega. So they made a bunch of patches in response to our attacks, our initial set of attacks, and they were not what we had recommended. So we thought we should take another look, and we managed to come up with some very cool attacks against the fixed version of Mega. And then, as like a side thing, just at the very, very end, we realized that these techniques could also be used to improve the original attack from 512 all the way down to 2 logins. So it was a very nice kind of evolution. And there was a nice competition between us and Nadia and her student Keegan. And I never want to be beaten by Nadia, so I'm going to make sure that we ended up with a better attack than what she and her team could do. And here I want to also give credit to Mega, right? They were when we
Yeah.
sent them an email, and within 6 hours, I think they'd responded saying, "We've read your paper or your disclosure. We understand the issues. We're going to fix them. We're going to work with you." And they gave us credit and they gave us bug bounties and they wrote very, very nice statements on their website about how honored they were to have been attacked by one of the strongest crypto teams in the world or something. Like it was perfect marketing, right? They played
Yeah.
it. They realized they were getting a free audit and they
Yeah.
used that in their marketing.
Yeah.
And I wish other companies maybe would learn a little bit from how they approached it.
Yeah.
It was very cleverly done.
Yeah, it's all to do with instant response and the message that you actually can portray. I think there was a recent data breach in the UK government
Hmm.
over Christmas time, and when you read the incident report, your head was spinning. You had no
Oh,
idea what was.
right.
It was all mangled. So I think
Yeah.
some companies can really use this as an opportunity to say that we really respond to ethical
Hmm.
hackers and we try to make our products better. Obviously,
Hmm.
for RSA 2K to factorize that, you would need all the energy on the planet
Absolutely. Yeah. Yeah.
and a
Yeah.
lot more to do it. So it's
To do
amazing
it.
that you could do it in two
Yeah.
login
Two,
attempts.
two
That's
login
just
attempts.
wonderful.
Exactly. It was
Yeah,
really, in the end, it's a really beautiful attack. It kind of
yeah,
combines all of these ingredients from, all of these like years of experience and insights and bringing it all together
yeah,
in one beautiful package. And
yeah,
it doesn't matter because actually the system had been fixed by that point. But at this point, it was just like an intellectual exercise. How low can we go? And so sometimes that's just, we just do that to kind of keep ourselves amused and keep ourselves off the streets, it's good.
yeah.
Mm.
When I look at cryptography code, I still see CBC and block ciphers, and I go,
Yeah.
why are you using this?
Yeah.
You should be using a GCM.
Yeah.
There's weaknesses, but my goodness, it makes it so much simpler
Yeah.
to use
Yeah.
these authenticated additional data
Mhm.
ciphers rather than the
Yeah.
old block ciphers. So I
Yeah.
think you've moved.
You also
Yeah,
have a much better API as a programmer,
yeah,
right? You have a very
yeah,
simple API that you can understand. You don't have to
yeah.
roll your own
No,
integrity. It all comes as a package.
yeah.
Absolutely.
Yeah, and Daniel J. Bernstein talks about the NIST competitions,
Hmm.
and he's quite critical of
Hmm.
them that they always go for high security, crazy security. We see things like Kitcha. crazy levels of security. Now we get Kangaroo 12, which is
Hmm.
reducing the number of rounds, and you've got like things like Blake that it's almost like for the NIST competitions, we fossilize things and we don't allow them to evolve. I've been looking at Aegis
Hmm.
ciphers, which are super fast compared
Hmm.
to AES, especially on accelerated hardware, but be really difficult to use them in industry because they're not in
Hmm.
NIST standard.
Gotcha.
So I think sometimes we fossilize and we
Hmm.
stick. Luckily, AES has been rock solid, but it
Hmm.
could be broken sometimes and overall. And I think you've moved your work towards recently towards Telegram, and I think
Hmm.
you co-wrote a paper, four attacks and a proof for Telegram. Uh,
Yeah.
how is it possible to have a proof if there are also attacks? Isn't that a contradiction?
Sounds like it, right? By the way, that title of that paper, we were trying to be clever there. It was meant to be a
Uh,
reference to four weddings and a funeral, but
Four minutes of advice.
I
Yeah,
don't think it
that's
works.
it.
I think Martin Albrecht, who's one of the co-authors again on that paper, was trying to get that, but
Yeah.
we didn't land that one. So we did this big analysis of how Telegram was using symmetric crypto. So you mentioned CBC mode a few moments
Mm.
ago. They used something called IGE, Infinite Garble
Oh
Extension.
yeah,
It's like,
yeah. I know your idea is
yeah,
quite old
yeah,
actually.
nobody
Very
uses
old.
it for anything,
Yeah.
right? And
No.
in their view, somehow this gave them extra security, and
No.
actually it doesn't.
Yeah.
It's like a relative of CBC somehow, a more
Yeah.
complicated version of CBC. So Telegram very much had rolled their own cryptography all the way down to the algorithm level, not just in terms of the protocol, but even at the level of base. Although they did use AES actually, but they were still using SHA-1 for hashing and
No
this
way.
data, and they were doing crazy things like deriving keys by applying SHA-1 with the
No.
bits in this order and then the bits in that order.
No.
Where
No
nowadays,
big
because
crypts or
we have
anything like
KDS, right?
that.
We have key
Yeah.
derivation functions. So
Yeah.
anyway, we thought it would be a good idea to start analyzing it. And this is actually a multi-year
Mm.
odyssey. So we published our second paper at Eurocrypt 25 last year, where we analyzed the key exchange part of Telegram, and we were able to prove it secure in some model. Um, and so it always leaves me a little bit icky thinking about Telegram because the cryptography is really bad. The problem is it has a billion users.
Mm.
And
Yeah.
if there's a billion users using it, we want to make sure that cryptographically it's reasonably sound, right? I mean, we
Mm.
might not like the cryptography, but if we can say something positive about it, then we should try to because it gives an assurance to those users. In some sense, the ship has sailed, right? It's too late
Yeah.
to do something different. So we thought it was going to be useful to analyze Telegram, and we did find some vulnerabilities, four different vulnerabilities. One of them is very practical. You could reorder the messages on the Telegram secure communications channel. If you were I think if you were the server, or maybe if you were a man in the middle adversary.
No. No
Yeah.
way.
Yeah. So they didn't
It's just
have,
crazy.
yeah, they didn't have integrity for the
Mm.
ordering of messages. And if you can change the order of messages, you can actually
Yeah.
change the meaning of a conversation.
Without a doubt.
Yeah. So we had the so-called pizza crime attack, which was like, shall we do pizza? Yes. Shall we do crime? No. And then you could change the order of the messages and, incriminate somebody, right? That was like a sort of slightly jokey example to show that, the message semantics can be changed if you can change the order of the messages. There was also a timing side channel attack,
Mm.
which was actually a reborn version of the SSH attack that we started this whole conversation with. It was very closely related. It was like a translation of the SSH attack from CBC mode to this IgE mode that they were using. And it exploited the fact that IgE mode is kind of related to CBC mode somehow. But it was a timing attack, so it was like a theoretical vulnerability, really. It wasn't really practically exploitable, but it showed that the underlying cryptography was like badly chosen. And then the other two attacks were actually against the handshake protocol, and they were ultra theoretical, but they also exposed the fact that they were not using state-of-the-art cryptography in the handshake, which is the thing used to agree all of the keys in Telegram. So that's all the attacks. Like, how did we do proofs? Well, we actually then said if you fix them in the following ways, if you make the following small changes to Telegram, then we can make the following security statement, like a security theorem, and prove something mathematical about the security. So Telegram actually did fix their system in response to our changes. That's a slightly bizarre experience when you disclose to Telegram. You
They
never
don't
learn
speak to you.
anybody's. Sorry?
They don't speak to you with their real names. No.
Exactly.
Yeah.
All you get is a response from Telegram security. And actually, there is some rationale to that, which is like, they're running a very large, globally deployed system.
Yeah.
And maybe their software engineers would be blackmailed
Could,
or
yeah.
bribed or who knows what to put
Yeah,
back
could
numbers.
end up in jail.
Could end up in
There's
jail.
been cases of people traveling to the US and they've been arrested because they
Hmm.
are writing cryptography code.
Right. Okay. Well, I won't be traveling anytime soon. To the US for sure. So yeah, so I can sort of understand it, but it was also a little bit like you felt like you were talking to, people who weren't real or to an AI or something. But anyway,
Yeah.
eventually they understood why this was important and they did make some changes in response to this. One of the things they did was they replaced the RSA encryption that they had in their key exchange protocol with their own homebrew RSA encryption.
No
Uh,
way.
so instead of switching to RSA OAP, they
Yeah.
kind
The
of
encryption.
adapted RSA OAP
Yeah.
to their own needs. Yeah.
No. Yeah. I mean,
Yeah.
obviously for key exchange, RSA isn't really seen to be a great, it's an
No.
encapsulation method, and I think it was dropped
Right.
in 1.3, although it's called
Yeah.
coming back with post-quantum
Post
cryptography,
quantum. Yeah, exactly.
unfortunately.
But
Uh,
the issue in TLS was that it wasn't forward secure. So if I could
yeah,
record your handshakes now and then break your key later, I could go back and learn all the secrets, right?
that's
And,
right.
and Telegram does have forward security because they use a weird combination of RSA encryption and Diffie-Hellman key exchange,
Mhm.
but not with elliptic curves, with mod P groups.
No
Um,
way. Oh, that's a crazy performance thing.
yeah, it's horrible for
That's
performance.
like 2K or 4K
Yep.
finite fields. It's that's
2K
the
mod
performance is
P
terrible.
Diffie-Hellman. Yeah, and that's still
Oh,
what it's doing today.
it's
And
like DSA signatures.
yeah,
Let's
it's
let's
it's
drop elliptic curve and go back to discrete logs again.
yeah,
That's
yeah,
and it sounds like it's all scrambled, but they've managed to get something that really works, and they have a lot of legacy, so they can't really dump it because
legacy.
they've got a lot of clients that they
Hmm.
would need to
Yeah,
update.
that's
I
right.
mean, compared, WhatsApp certainly seems to be one of the best and around for that. Telegram has always been a bit vague in what's
Hmm.
going on underneath.
Hmm.
Signal too, there has been some worries about that one, but
Mm.
yeah, it'd be interesting to look at some of the
I,
other ones too. I don't know if
yeah, well,
they're on your agenda.
yeah, definitely. And other researchers are doing that too. Lots of people have looked at and proven things about
Mm.
Signal. Signal is the one that cryptographers actually love, that we really
Yeah,
think is strong and good.
it's the
Um,
ratchet mechanism.
yeah, double ratchet plus
Mm.
just also they're very, very responsive when you do find
Mhm.
something that's problematic. You can talk to people and get things fixed very quickly. They actually have a guy now called Rolf Schmidt, who
Mhm.
his job is to go out and talk to the academic community and work with them
Wow.
to bring them closer together, and he's doing a fantastic job. You'll see him. He's I think has something like 4 or 5 presentations at Real World Crypto this year in Taiwan. So he is like the single most prolific person I think now because obviously Signal has all these really interesting cryptography problems to solve, like how do we get to post-quantum? And then there's lots of cryptographers in academia who want to help them because they're a great organization and we love the Signal design. So it's just great. It's a really really nice coming together.
But we still have crypto wars. I mean, crypto wars has never gone
Never
away,
gone away.
and really, it's probably even worse
Yeah.
now. And as I said, I mean, someone who's working in this field could be arrested quite easily because they're
Hmm.
defending bad people and bad states and so on. So it's one that you can never win. I think Australia is one of the most extreme, and it's funny that the UK is
Hmm.
also right up there in terms of
Absolutely.
trying to break cryptography, which
Yeah.
seems quite surprising. So
Yeah.
it's an everlasting war that goes on overall.
Overtly
And
and covertly. Yeah. And it
yeah,
could be it could be that we're past the best days
yeah,
of cryptography in the sense that it
yeah,
becomes more and more regulated and
that's right.
enforce backdoors and so on. Let's see.
Yeah, agentic AI is going to be agents that are holding our encryption keys and our passwords.
I
That's a
don't like the
scary
sound of
thing.
that. Don't make me
Yeah.
do that.
No,
Don't make me break all those systems as well. Come on.
I know, yeah. So we're obviously moving towards post-quantum cryptography.
Yep.
So we love RSA. RSA is amazing, 1977, and we've used it all the time. It's still the
Yeah.
most popular method used for signatures for trust on the web. And we obviously have elliptic curve Diffie-Hellman. We just love that, but they're all going to be cracked by quantum computers. So we're now moving towards ML Chem and ML DSA and the other one, SLH DSA, I think it
Hmm.
is. And it's coming up with a few other ones. Hopefully, we might even see
Hmm.
Macaleese, I think, sometime. But
Hmm.
obviously, the problem, it's taken us decades to secure these existing methods for side channels. Do you see a can of worms opening up as we start to implement these post-quantum cryptography methods that we haven't really secured lattices yet and for side channels?
It's a great question. I mean, specifically for side channels, I guess there have been some quite notorious or famous side channel attacks already against post-quantum algorithms. Usually against like reference implementations. Maybe as we go more towards production implementations, we won't see so much of that. But I think the reason I'm saying that is because although some of these algorithms are more complicated to implement, they actually have quite a few sharp edges that you can catch yourself on, depending, like for example, the Falcon signature scheme has like floating point arithmetic kind of built into it, and it's hard to avoid. And that's like
Yeah,
a huge
B50s.
source of problems, right? Can be.
Yeah.
But I think as well, the crypto community broadly, not academia so much, but like developers, people who are building crypto libraries and so on, have learned a lot over the years about what can go wrong. And there's a lot of experience now, a lot of folklore knowledge and formalized knowledge, a lot of verification tools as well that we can use, for example, to guarantee constant timeness. Um, and so I think there will be problems, but I don't think it will be this like multi-decade epic journey that we've been on to protect existing crypto against side channel attacks. I think we'll accelerate it because I think we know more now. We're starting from a different starting point from where
Yeah.
we were.
And do you worry about learning with errors and lattice-based cryptography? So there's obviously strong hash-based methods. Sphinx Plus
Mm-hmm.
is a very strong because Merkle trees have been around and
Forever.
hash
Yeah.
methods are as near provable as we can get. But
Mm-hmm.
learning with errors, there's still some worries about them. Do you think they're actually going to be secure for the next 5 to 10 years?
I think the first thing I would say is I'm not an expert.
Mm.
And you've had the experts on, right? You've talked to people like Martin Albrecht, maybe I don't know who else you've had, Vadim Lubajczewski, Chris
Chris
Kuiper, there
Packard.
you go.
Yeah, yeah,
So I would refer your listeners to or your viewers to their answers to that question. I'm not really in the same. So that's one of the things about cryptography these days. It's kind of fragmented, right? You become an expert in this kind of ever decreasing niche, and like LW, I'm here, and LWE is over there somewhere, like on the edge of
yeah,
the screen, and I just kind of wouldn't like to say. I do. The thing that keeps me awake at night is that there might be a quantum algorithm that can efficiently solve LWE for the instances that we use in cryptography. So far, that hasn't happened. There have been some false alarms, every couple of years. Somebody comes up with something that might be a quantum algorithm for solving LWE. There's some recent work on trying to use machine learning to solve LWE problems. I think it should be ignored. I think it's been a little bit controversial in the cryptography community because they don't really work with parameters that we use actually in cryptography, and um, there are like known classical algorithms not using machine learning that can solve those instances much more efficiently. So you can say, well, but it's the early stages and maybe it will develop, but it's kind of alarmist to say, oh, machine learning is going to break LWE. But quantum algorithms, yeah, it's really hard to be definitive about that. There could be an idea just around the corner. But cryptography is always like that, right? Like we
yeah.
do our best. We try to hedge against obvious attacks. We work very hard try to certify what we're doing in the sense of trying to break it. And if we can't break it as a community, then eventually confidence grows. And there is no alternative, right? Because until we can prove that P is not equal to NP, that's the kind of situation that we're in, right? Maybe there is no efficient cryptography, maybe public key cryptography. Maybe P equals NP. I doubt that very much, but anyway, I digress a little bit. I just want to say that cryptography it lives in this world where inherently it's uncertain. Um, and there are people who would like to bring certainty. Like one of the big ideas behind things like quantum key distribution is that you only have to rely on the correctness of quantum physics. Um, the reality is different because they have to deal with side channel attacks and all kinds of, quantum hacking and all that kind of thing. Uh, it's just that is the world that we live in as cryptographers. You have to learn to live with that uncertainty that tomorrow somebody might find an attack against your system.
Yeah. And obviously, a dream for database companies is that you can encrypt all your data blobs,
Hmm.
and you can use some sort of searchable encryption to be able
Hmm.
to find the data or to find the
Hmm.
blob that you actually need. I know that companies like Google uh, really need that type of approach, and Apple are
Hmm.
using that type of thing. Typically, it
Hmm.
involves pairing-based cryptography and usually some sort of public key cryptography. But I think you looked at searchable symmetric
Right.
encryption. Could you just explain roughly how that works?
Yeah, sure. So the idea of searchable symmetric encryption is to be able to, let's say, outsource the storage of your data in a secure to a server that you don't trust necessarily, whilst maintaining the capability to search over the data. So the data is now sitting on some remote server, and you have to be able to send some kind of query token to the server that enables the server to do some computation and then send you back some answers that tell you maybe which documents contain a certain keyword or which of your collection of strings contain a certain substring if you're doing, say, substring search, right? So there's keyword search, substring search. You can have range queries. Eventually, you'd like to do all of SQL, for example,
Yeah.
like kind of some standard database query language in this kind of encrypted search domain. The symmetric crypto part is there really for efficiency. So we would like to be able to do this using only symmetric key crypto techniques because generally speaking, they are some orders of magnitude faster than public key techniques. And here we're thinking about very large data collections, right? Like, terabytes of data maybe that we want to be able to outsource and search over. And I talk about the outsourcing scenario, but it's also relatively important nowadays to think about um, what happens if your organization suffers a data breach and or maybe you have a persistent attacker who's able to access your infrastructure as an organization, as a company, as a university. And so what you would like to do is maybe keep as much of your data encrypted at rest as possible, and then be able to not even decrypt it when you want to work on that data, right? And so that leads to concepts like fully homomorphic encryption. But searchable encryption or symmetric searchable encryption is the version of that purely for search functionality. And the idea is just to make it super efficient. So actually, I was just today I've been working on a paper which looks at the security of some substring searchable encryption schemes. And we noted there that there are some solutions out there that use fully homomorphic encryption, but they take like tens of seconds to handle a single query on a very small database. Whereas we want like sub-second answers on gigantic databases, terabytes instead of 1 kilobyte, for example. So that's what symmetric searchable or searchable symmetric encryption is all about. And the current state of the art is that we know how to do this relatively efficiently for simple search capabilities, like keyword search. Give me all the documents containing the word Bill or the word Kenny. But as soon
Yeah.
as you want to do something more complicated, like give me all the documents containing Bill and Kenny, then it becomes much harder.
Yeah.
And the paper that we're writing right now is actually showing that three of the state-of-the-art schemes for substring searches are actually insecure. We can break them all. Fortunately, as far as we can tell, none of them has been deployed anywhere yet. Hard to tell completely, but it seems like they're just, they exist really as research papers at the moment. but they're published in quite high-profile venues, never really been properly cryptanalyzed, and we're the first people to really to break them actually. So coming soon to a conference near you.
That's great. Yeah, because I've seen ordered
Oh yeah,
encryption,
order
and
preserving
that's
encryption. Yeah.
order preserving, but it's not that secure. You can say
No.
if X is greater than 100, if the age is greater than 53 and less
Yeah.
than
Yeah.
90, then these are the records, and you can give the
Exactly.
encrypted records back. But I
Yeah.
think it's really difficult to have strong security because
Yeah.
you will leak information there.
Exactly. And so the art is here is to somehow reduce the leakage down to an acceptable level that somebody like me can't break it without compromising the efficiency too much, right?
Yeah,
And we're still exploring that kind of frontier of what's possible. And actually, order preserving encryption was like a step too far in the sense
yeah.
that the functionality itself actually leaks too much.
Mm.
And there are quite trivial attacks against OPE schemes. So they really shouldn't be used in practice, although they're very appealing and very
Okay.
tempting, but you shouldn't really use them. So
Mhm.
it's a really interesting developing area. It has started to see some deployment too. So in 2023 or 4, MongoDB launched a product called Queryable Encryption,
Mhm.
which is allowing you to do queries over or searches over encrypted data in a MongoDB database.
Yeah.
Um, so yeah, unfortunately, we broke the first version of their scheme. But okay,
Yeah.
they've improved it since then, and they're a little bit more careful about what security properties they claim for it in their documentation now as a
Yeah.
result of our work.
I mean, there's obviously partial homomorphic encryption using
Hmm.
traditional discrete,
Hmm.
using elliptic curves
Hmm.
that can be used because a lot of the calculations are subtraction
Yeah.
or a basic square. Like if you're looking for the difference between two vectors, like in a
Hmm.
biometric type thing, you can use
Hmm.
partial homomorphic encryption for that, and that has better
Totally.
security. You can use Palia and things like that.
Yep.
So I don't think we
Yep.
need to necessarily move to full homomorphic encryption for
Yeah,
everything. There's still some
that's right.
nice partial homomorphic encryption methods, and I think designers need to sit down and see what is it we're doing. All we're
Yeah.
doing is subtraction or differences in vectors,
Yeah.
and obviously when we're teaching, we'll have to move away from the methods for elliptic curve and discrete logs and move
Yeah.
towards polynomials and
Yep.
lattices and things like that. So that's going to be an interesting time for us.
It
So
is. As teachers, I wanted to ask you, I mean,
yeah,
when you
yeah.
teach cryptography, at what point will you stop teaching RSA?
I love it. And I'll spend 15 minutes asking the audience to give me a P and a Q, and
Hmm.
then I'll tell me an E that doesn't work. Okay, we'll use this E. And then in Python, I just do D.
Hmm.
And it's just in Python, it's just pow to the E to the minus one mod n
Hmm.
uh, mod phi, sorry.
Hmm.
And then I'll show bit by bit, and then that magic of revealing the original number, I think, is
Yeah.
just wonderful. It's like being back in 1977 when Martin Gardner released the Scientific
That's an
American
article. Mm.
paper. I
Yeah.
mean, that just sparks so much interest, and I think it's
Mm.
still theory. And just
Yeah.
because it's broken doesn't mean that the theory goes away.
Hmm.
And I think as a researcher, we should always look even at the old methods that they might come alive again. So
Hmm.
I do love it, and I love showing Diffie-Hellman. So I'll
Mm.
probably still teach these things, but then I'll obviously have to think about how to teach these other
Yeah.
techniques. The Merkle one is good because the hash-based approach with the Merkle root is good because that works quite well with blockchain teaching.
Hmm.
So
Hmm.
certainly probably more of the hash-based things. But I think you've got to try and interest your students and really try to get them engaged in the subject. And I
Right.
think if you get too difficult too
Yeah.
quickly,
Too quickly.
then it can become difficult. So
Hmm.
you've worked in lots of areas, lots of places.
Hmm.
Bristol, as you said, with HPE, and then in London and in Zurich. So, which place would you say that you learned most from?
Mm. I think I learned very different things in the different places, and maybe those things are not really comparable to each other. So, for example, when I worked for HP Labs, I really worked as a kind of mathematical consultant.
Mm.
And during that time, I think I learned how to talk to engineers. And eventually, as well, working there alongside me was Nigel Smart and also Stephen
Yeah,
Galbraith.
Bristol.
I learned a lot from them
Mm.
about how to do research and about getting back into cryptography and making that my main focus. So I also had my first go at management at HP Labs. So I spent 2 years as a project manager there, which was tough times. I learned a lot about myself and about other people, and so I think if you had to ask me for one place, I think probably HP Labs was the best for me because it forced me to also think more about the real world out of academia. It was good to spend 5 years in industry even though it was a research lab and I could still do research, I was tasked with talking to engineers and solving their problems mathematically. So I think that gave me a kind of broader perspective on what mattered in the world beyond the kind of the so-called ivory tower. But like coming to ETH and being head of department for 2 years was absolutely mind expanding.
Wow.
Figuring out how the university works and how finance works and how to keep have all of these really top people at ETH in terms of like their scientific contributions. But like, how do you get those people to teach, right? When they all want to be flying around the world, so there's a lot of good challenges there. So I think in every place I've been, I've developed and learned things, and it's been a great adventure, I must say.
Yeah. I speak to a lot of cryptographers, and a lot of them have spin out companies and
Hmm.
startups. And you'll find, especially in the US, their skills
Yeah.
are in such high demand. Nigel Smart is a good example of
Hmm.
that. Jens Groth, I
Hmm.
think, is obviously working for a big blockchain
Hmm.
company. And you'll see the people in MIT and Stanford are all looking at spin out and startup companies. Is that
Hmm.
something that's on your agenda for the near future? Do you see yourself spinning out a company from ETH?
It's a great question. I think that it very much really depends on the appetite of, say, my PhD students and master students and what they want to do. I don't think I would be the one to spin out with them and be a founder or be a CTO or something. I'm more likely to be in an advisory role.
Yeah.
And I've done that role for a number of startup companies. There's one in London that I still work with from time to time called Crypto Quantique,
Mhm.
which was founded by a graduate from Royal Holloway called Sharam Mosayebi, or co-founded by him.
Mhm.
And they're doing really cool stuff with puffs, physically unclonable functions,
Yeah.
based on quantum effects in silicon.
Moti Young. Moti Young. Yeah. Yeah.
Well, he's with Google now. Yeah,
Yeah.
yeah. Crypto Quantique was the name of the company.
Yeah.
So anyway, I've done a little bit of that, but I've never fully committed to in the way that other people have to saying, okay, now I'm going to make that my 100% thing, and I'm going to take the risk and see whether we succeed or fail. And for some people, it's worked really well. Some people get to retire early and fly around the world, following the Rolling Stones on concert or whatever it is that they want to do. Um, I also just loved spending time tinkering around with cryptography, and I think if you go into a startup, there's all the obvious pressures of actually building a product, raising capital, and finding the right people to work for your startup, and um, I think that's maybe not my natural skill set. I do a lot of consulting work as well, so companies come to me and say, we need X, or we want you to evaluate Y. And then, it's like a limited term engagement where you're taking much less risk, you're not taking equity, but you're getting paid with a nice day rate. And ETH allows me to do that. It has a good system to allow its academics to do consulting work.
Yeah, I think there's a recent paper in Nature that outlines that it's a very healthy thing. The number of consultancies in the UK for academics is reducing, but the value is actually increasing. And it's a very
Right.
healthy thing in academia to have
Hmm.
links with industry. Obviously, they have the problems, and it helps to inform the research overall.
Hmm.
And so, what does the next decade look like in cryptography?
Well, we have this post-quantum transition going on, and I think that will raise a few surprises for us along the way. I think there's also this big emphasis now on more advanced cryptographic functionalities like fully homomorphic encryption that we discussed, or searchable encryption, or private information retrieval. So these kind of more sometimes people call them fancy cryptography, right? So beyond modes of operation, beyond AEAD and key exchange towards privacy enhancing technologies based on cryptography. And there's a lot of I see a lot of potential in that area, both to develop new techniques and make these things more usable, but also bringing this cryptography in the wild kind of approach to that. So as they become more deployed, there'll be more cases where they're being used and maybe misused, and then more opportunities for people like me to look and dig in and see what we can find. So I think the future is very bright.
Yeah. And obviously, Switzerland is such a wonderful country, probably one of the best places in the world to live. Is there anything
Mhm.
that you miss? Obviously, not the weather from the UK, from
Well,
Scotland.
yeah, I mean, there's just Switzerland is a very rich country and very well organized. I would say there's a lot of expats, or how could I say, immigrants living in Switzerland, so non-Swiss people living in Switzerland. Particularly in Zurich, it's incredibly multinational, and ETH particularly. So it's like a bubble within a bubble. Um, it is a little bit hard to get to know Swiss people,
Mm. Yeah,
because not because there's so few of them around, but because you arrive and they already have organized their lives and have have their social clubs or their tennis club or whatever. And so I miss the kind of like really, how if you go to a pub in Scotland and you see two guys and they've both got a pint of heavy and they're drinking, it might sound like they're about to break into a fight with each other, but they're actually just having a conversation.
yeah,
And I miss that a little bit, I would say.
yeah,
It's a difficult thing to replicate here in Switzerland, I would say.
yeah.
So there's something about Scotland and the way Scottish people interact with each other and the very, very strong sense of community that exists in Scotland, I think is a little bit more, it's a bit different here, I would say.
Yeah. Yeah,
Mm.
I think certainly cities like Edinburgh and Glasgow are quite internationally focused and increasingly,
Mhm.
and we have a lot of students that
Yeah.
come from all over the world.
Mm.
Unfortunately, it's reduced from an EU point of view, but I think a lot of people really still prize coming here and living
Hmm.
in these great cities. So
Absolutely. Absolutely. Yeah.
you've probably got the best of both worlds to be
Maybe
able to come
so.
back
It's a short flight,
to
right? Yeah. And I still have
to
family living in Scotland, so I have good reasons to
That's
visit.
great.
Yeah.
Okay, my last question. Well, let me ask one more question, my
Sure.
penultimate question before the last one, and
Yeah.
it's obviously a thorn in our hoofs. Actually,
Hmm.
is the whole thing around patents. Uh,
Mm.
so there was the RSA patent that didn't. MIT were quite aggressive in following it up, and RSA did evolve, but there
Yeah.
are other areas like this, the Klaus Schnorr patent for
Hmm.
signatures that really
Signatures.
didn't
Yeah.
advance. So
Hmm.
I know that you're not on the patent side necessarily. Is there a place for patents in cryptography? What's your belief?
Right.
Should early career researchers be patenting their amazing discoveries before they publish? How does ETH see these things too? I mean, obviously they're built on intellectual. The whole university is built on intellectual property and income
Mm.
generation. And
Hmm. Hmm.
are they looking for patents from researchers? What's your feeling about patents
Yeah.
and cryptography?
So I'll maybe focus in cryptography rather than the broader question of what's the ETH policy or whatever.
Mm,
But I I understand why people file patents and
mm,
why they want to found maybe companies based on those patents. Although that's actually less and less important. I think it's more
mm,
about the people that you have and how quickly you can build a product and scale it these days than having the right patents. So I think the net effect of patents in cryptography has been to slow down the adoption of cryptography. Um, in the early 2000s or maybe late 1990s, there was this company called Certicom, which had lots of patents
yeah,
or patents on elliptic curve
yeah,
cryptography.
yeah,
And the way they used those patents just frightened companies. And I was there at the time, and it made my company, HP, really hesitate to do anything with elliptic curve cryptography because you just didn't know what kind of shitstorm you were going to walk into.
yeah, yeah,
Um, And I think in the end, that was actually bad for Certicom because I mean, I understand that they needed to defend their portfolio and they saw that that was their strategy for growth was to license the patents. And in the end, it worked because they licensed them to the US federal government, NSA. And so it worked for them in the end, but it really made elliptic curve cryptography kind of toxic for a long time. So I think the net effect of them has been negative. Um, but I also understand why individuals and companies want to have them and want to protect their inventions and they maybe see it as a way of monetizing the invention. So I think it's one of those things where it's not so clear cut, but overall I prefer that we didn't have patents in cryptography. And I know that there are like lots of organizations now, particularly standards organizations, that are for whom patents are like a kind of no-go. So this was a huge issue during the NIST competition, right? And the patent situation was unclear, and a lot of time and energy was involved in trying to resolve it. And payments were made, and licenses were agreed, and the situation eventually, I think, is more clear now. But it caused a lot of stress, and I would rather avoid that.
Yeah, when you think about it, Neil Koblitz, Victor S. Miller could have made an absolute fortune
Maybe
in their papers
in their
and
papers, but
in yeah,
it still took 20 years from the
yeah.
invention of elliptic curve cryptography to widespread deployment, by which time their
It's
patents might have expired, right?
expired.
Unless they had
It's
clever patent lawyers who knew how
yeah,
to extend the life of patents. By the way, you said I'm not in the patent game, but I used to be.
yeah,
So if you
yeah.
look on,
Uh,
if you look, I actually have multiple patents from my
ah,
time in industry because they
from
are
HP. Yeah,
from HP.
HP are obviously quite aggressive, and
Yeah,
IBM and
yeah.
these companies, Intel are.
Exactly. It was a big part of our job to write up these ideas, as well as writing research papers, actually patent the ideas. So
Yeah.
I
But you don't
had a
get any
portfolio.
money to
No,
be an author. That's the
no.
crazy thing. Whoever owns it actually makes
But
the money, and whoever wrote it gets nothing.
exactly.
It's a
But we
crazy
did have a
system.
nice system at HP where you got a little bonus if one of your
Ah,
ideas ended up being filed.
is that
Uh,
right? Because I know
yeah.
that IBM have they have some rewards, and obviously you can get promotion based
Yeah.
on it. And you can even get a PhD eventually. I know some universities take credit for people writing patents
Hmm.
with an IBM, and they'll eventually get their PhD based on the patents that they wrote
Okay.
over like a 10-year
Hmm.
period. But yeah, it's an
Hmm.
interesting space, and
Yeah,
you
definitely.
just worry that it's the big companies that always benefit, and they're exchanging patents to give themselves that
Hmm.
advantage in the marketplace.
Hmm.
And my last question is that you've had an amazing career, and I think anyone who's an early career researcher can actually look at your route and the choices that you've actually made. And I think that industry part was been really key for it. But if you could change one thing about your career, what would it have been?
Oh God. You know, there was a point where I'd done two postdocs, one in Zurich, actually at ETH, and then the second one was back at Royal Holloway.
Mhm.
And I was applying for academic positions, and I couldn't get one. And I was offered a postdoc in Israel to go to the Technion, which is a really strong place.
Excellent. Yeah.
But it was a 1 year postdoc, and it was the salary was like $1,000 a month. So my salary has actually decreasing over time as I went from ETH back to Royal Holloway and then this offer. And I don't think it was a bad decision to go to HP because, as I said, it's one of the places I learned the most. But I wonder how my life would have been different if I had gone to the Technion for that year. Because it turned out, I found out much later that the host professor there was already talking to people in the US about this guy that he might send over a year later once he'd spent a year, i.e., me, after I'd spent a year in Israel. So maybe I would have ended up working in Silicon Valley in the 1990s and the 2000s. So it's a kind of a sliding doors moment where it's hard. I can't regret it because I just have no idea how it would have worked out. But you get faced with these choices, and it's not always clear how to make the best choice. So
Yeah.
maybe to answer your question really explicitly would be I would like to have better decision-making capabilities.
Yeah, well, I think we would all like to have that.
Or
But
a
I mean,
bigger brain. I would also ask for a bigger brain.
you've ended up at the best university in the
Oh, I
world for
know.
this area, and in one of
Yeah.
the best countries in the world. I think what you've really done is an inspiration. It just shows you that maybe you don't want to get stuck in one institution,
Yeah.
and really sometimes you want to move outside your comfort zone and
Yes.
just push yourself somewhere else.
Somewhere else.
But
Yeah. Hmm.
I think the way that you've progressed has been really amazing and an inspiration to anyone, any researcher. Obviously, it's going to be a difficult time for researchers coming up with Gen AI, and it's
Hmm.
just such a changing
Hmm.
area for
Yeah.
teaching and so on. I think universities are really going to have a tough time overall, and obviously things like the peer review process is becoming more difficult
Yeah.
with Gen AI. I see papers now that increasingly peer reviews are done through Gen AI and not
Right.
through humans. So
Yeah.
we're moving into a world that might be a bit dehumanized. But the
Absolutely.
great thing
Absolutely.
is that the core principles are still all there. So
Hmm.
thanks very much for taking 2 hours nearly of your
Wow.
time, and
Okay.
all the best with your new role,
Hmm.
which won't involve as much admin, and we'll be looking out for your papers. So
Thanks
thanks
a
so
lot,
much.
Bill. Pleasure to talk to you. Thanks for your time.
Thank you.
Thank you.